Okay, we are live now. Thank you. You can go ahead.
Thank you.
Thank you. Okay, welcome to the pizza seminar. This week's speaker is Isaac Tutusaus. Isaac got his PhD in 2018 from the University of Toulouse. Then he came here at the ICE to do a postdoc. Then he went back to, well, no, he went to Geneva for another postdoc. Then he went back to Toulouse. And finally, in 2025, he came back here with Ramon y Cajal. And since this year, he's a científic titular. So, well, you can go ahead. The floor is yours.
Thanks, Ramon. Well, thank you. Yeah, I thought it was a good opportunity to give a talk and to present myself to people who don't know me yet. And I wanted to do this by talking about Euclid. So this will be a cosmology talk. And the idea is how we can combine different cosmological probes to basically be able to constrain cosmology with Euclid. Now this, of course, doesn't work, but oops. Yeah, good. So this is the outline of my talk. I'll first start with a brief introduction, basically talking about cosmology in general. Then I'll basically tackle what's the core science of Euclid. So what are the main cosmological probes we're interested in, what we are going to do to basically extract information from Euclid observations. And then I'll say how we plan to combine and why it is important actually to combine different cosmological probes to extract the best possible constraints. Then I'll just say a few words about going beyond the main probes. So why it's interesting to add even additional probes into the analysis. And I'll basically spend the last part of the talk saying what has happened since the launch in 2023 until now and how we're preparing for the first analysis, or the analysis with the first data release. So we know that the standard model in cosmology is what we call lambda CDM, so basically constant, cosmological constant and cold dark matter. And the reason for that is because this model has been able to reproduce the main cosmological observations for a few decades already, which is quite impressive. Now in this model, we know that roughly 70% is dark energy, 25% is dark matter, and only 5% is the standard matter that we know that we have here on Earth that can be basically distributed depending on whether we have cold intergalactic gas or we have stars or we have different types of intergalactic gas, warm, hot. But there are a few problems with this model, which are very well known. First, the nature of these main components remains unknown. So we still don't know what dark energy is. We still don't know what dark matter is, which is 95% of the universe. Therefore, we have a problem. And there are also tensions that start to appear. And this is now a very exciting moment, actually, because the latest data, latest meaning like since then, 2024, especially 2025 was a very nice year for that. There are data sets that show that there is a preference for evolving dark energy. So this is a very exciting moment because it's the very first time in several decades that we find something that's pointing away from lambda CDM. So there might actually be something beyond the standard model. Now, I just wanted to, as introduction, to basically set up the scenario, just wanted to mention different tensions that are very important in cosmology nowadays. One is the Hubble tension. So when we measure the expansion rate of the universe, we can do that in a direct way. You see there are plenty of different ways to do it. Most of them depend on Cepheids, but there are also other ways. And they all find quite a high value, around 73 kilometers per second per megaparsec. Now, of course, all these methods will suffer from different systematic effects. But then, on the other hand, we can say, well, let's just look at cosmology. Let's just look at early times, for example. Let's just look at the cosmic microwave background. Let's assume the standard model, and then we derive the Hubble rate today. And then we get this 67 value, which is significantly smaller. Now, this is from a paper that was published. IEEC was also involved in this, if I'm not wrong. It was published like this month or last month. And I think it's the most updated version of this plot showing the tension. And if you look at the consensus here, the baseline, and you compare against the CMB, we have more than 7 sigma. So if you talk to a particle physicist, they will tell you 7 sigma, that's a Nobel Prize. But here we still don't trust it that much. Now, there is another tension, which I don't know whether we should call it tension or just slight discrepancy. I can see Alex nod saying no over there. So for many years, if we measure S8, that basically tells us about the amplitude of matter fluctuations versus the matter density, we see this blue contour. This is coming from early times, again, cosmic microwave background, assuming the standard model. And then all these other contours, these are using weak lensing surveys. And this is from this very nice paper by the DS collaboration that many people here actually wrote. So the interesting thing is that the weak lensing contours seem to be always lower than what CMB would like. Now, one thing I wanted to mention is this bluish one, the Kitt's legacy. This is interesting because for almost a decade, they've always found something like 3 sigma tension. They were always quite well below CMB. And in the legacy analysis, they actually got compatible with Planck. So now a lot of people in the community thinks that there is no tension anymore, but others still think that it's important to understand why there was a tension at some point and why it seems to have disappeared. But anyway, let me just move to the next one, which is actually the most recent tension, let's say. Now let's try to go beyond the standard model. If we want to go beyond the standard model, instead of using cosmological constant for dark energy, the simplest thing we can do is to use a phenomenological approach, and we model dark energy as a fluid. Now, once we have dark energy as a fluid in the cosmos, the easiest thing we could do is to take the equation of a state parameter, and just assuming it's a constant, we just Taylor expand it. That's what we do here. We model dark energy as a fluid with an equation of state parameter that basically has 2 terms. W naught is the value today, so it would be -1 in lambda CDM, and WA is basically telling us how this equation of state varies as a function of time, it's a function of redshift. Now, the DESI collaboration last year, they did this analysis where they combine data from DESI, of course, coming from large scale structure, cosmic microwave background, and you see 3 contours correspond to the 3 different data sets of type 1a supernovae. And once you combine everything, you see that this cross here, this is -1, 0. So this stands for the cosmological constant. And you see that it's like a 3, 4 sigma preference for evolving dark energy, depending on the exact sample for type 1a supernovae that you use. So now this led to like hundreds of papers trying to explain what could lead to this discrepancy. So, but it's very exciting. It's the first time we see something going away from -1, 0. So we want to better understand whether there's an evolution for dark energy or not. So we are at a very special moment. Traditional cosmology will now really benefit from all the investment that has been done in very large projects. And I wanted to talk about Euclid. So here you see, this is an artist's impression. I have pictures afterwards, but this is an artist's impression of the satellite. And this is the largest European project for cosmology, of course, with very significant contributions from other countries like the US, Canada, or Japan. And its main goal is to do cosmology. It will be used for a lot of legacy science, but its main goal is to provide very precise measurements to try to shed some new light into these dark components of the universe. And in order to do that, in Euclid, different probes will be considered. So let me just emphasize what I mean by that. So we know that combining different cosmological probes is basically the best way we found so far to constrain a cosmological model, because different probes usually are sensitive to different aspects of how gravity actually acts in the cosmos. And by combining them, we can break different degeneracies between the parameters and also between different systematic. So probes usually suffer from different systematic effects. So by combining them, we can improve the overall constraints. And I like this plot also again from the DESI collaboration very much because it shows the power of probe combination. Here you just see the equation of a state of dark energy versus the matter density. In this case, it's just a constant. So -1 here would be lambda CDM. And then you see this blue contour, that's large scale structure. So DESI can put nice constraints on matter density, but okay-ish constraints on dark energy. Then we have type 1a supernovae, which are these contours here, and we have the CMB, which provide very complementary constraints. And it's just when we combine all of them that we can break these degeneracies, and we get these tiny contours in orange here, putting very tight constraints on both the matter density and dark energy. And I also wanted to show this plot because it's more recent, again, from the DS collaboration. This is basically the kind of state of the art. Here you see in this pinkish color, the 3x2 point. I'll say what that is, but Martin already said this a few weeks ago. From DS, and if you combine with different probes coming from the cosmic microwave background or low redshift, again, you get these super tiny contours. So really, we are interested in combining different cosmological probes. Now, Euclid started on Valentine's Day, 2024. So the main survey started at that point, and it became at that moment the very first stage 4 weak lensing survey in operations. So the first stage 4 spectroscopic survey was DESI, but Euclid was first in terms of photometry. And it will cover around 14,000 square degrees of the extragalactic sky. So here you have the full sky. You can see the galaxy here, and this would be the ecliptic plane. All these patches, this represents what Euclid will observe in 6 years. So year number 1, this is green. You see it's like 1/3 in the north, 2/3 in the south. And then as a function of time, we'll get closer and closer to the galaxy. There are 2 instruments on board Euclid. One is VIS, that's the visible instrument, and it does imaging. And the other one is NISP, which is the near infrared spectrometer and photometer that does both imaging and spectroscopy. So schematically, the idea is the following. Here we have our universe, cosmic web. Light will enter into the telescope, and once it reaches inside the spacecraft, it will be split between visible and near infrared wavelength. So the visible one will go to VIS, that will take images, and this basically produces very high resolution images. And the near infrared one will go to NISP, that contains both, can produce both photometric and spectroscopic measurements. So we will use this instrument to determine the redshift of a lot of objects. Now, one thing it's quite important to keep in mind, and I go back again to this combining stuff idea, is that Euclid actually needs to combine already from day 1. What I mean by that is that this is the transmission as a function of the wavelength that we have in Euclid. You see this blue, very broad band here. This is the band that we have in VIS. So this means that we have a very broad band, and that's great because it allows us to go very deep very quickly. So we take images, it takes just order 30 seconds, and we go super deep. And it provides high resolution images. Now we also have these 3 bands in the near infrared from NISP, and we have these 2 distributions here that are the grisms that we use for the redshift. Question is how we determine the redshift if we are lacking information in the visible range. Euclid cannot provide measurements in different bands here. And if we don't have those measurements, it's essentially impossible to determine or estimate the redshift of the galaxy. So we have spectroscopic here, but that's just for a subset of galaxies. Now, for all the other galaxies, we do not have information here. So what we do is we combine with ground-based data. So we use telescopes on Earth that can provide measurements in all these bands here that we're missing, and we combine everything to determine the redshift. So that's why not even just probe combination, but actually combination of data is a key ingredient in Euclid. Without relying on the ground-based data, we cannot carry out our cosmological analysis, or not a large fraction of it. Good. So that was the introduction. Let me just move to describe a little bit the core science that we are trying to do with Euclid. So the first thing is what we can do with spectroscopic data. And that's spectroscopic galaxy clustering. So there are two things. One is BAO, so baryon acoustic oscillations. Now, if we go back in time, when the universe was a hot and dense plasma of baryons and photons, this plasma was oscillating because basically gravity would pull inwards and radiation pressure would pull outwards, and there were oscillations. But at some point, photons decoupled and they could start to propagate freely, and we see them as the cosmic microwave background now. But the thing is that these oscillations froze and they kept propagating till nowadays with the expansion of the universe. Now, what that means is that if you point at the galaxy and you look for the probability of finding another galaxy at a certain separation, there is an excess of probability at a given distance, which corresponds to the size of these oscillations back when the universe was very young. And this is exactly what you can see in this plot. So here, well, we see the monopole of the correlation function, some details, but basically this is telling you the probability of finding galaxies at a given separation. And you see there is an excess here. There is a peak. So this is the peak of the baryoacoustic oscillations. Now, if we measure this peak, we can link it to the early universe, and we have what's called a cosmic ruler. So we have a given size, physical size, and we can basically measure how this size expands as a function of time. So this allows us to probe the expansion of the universe and to basically determine distances, which is the most complicated thing in astronomy. Another thing that we will do with the spectroscopic data is to look at redshift space distortions. So now if we go back to these oscillations, they are isotropic. The thing is that we do not observe galaxies in real space. We always observe them in redshift space, which means that if galaxies have peculiar velocities, they will distort this isotropic shape. And this is exactly what we see here. So this is nova density, and basically galaxies, if you look at this is the correlation function along the line of sight and perpendicular to the line of sight. And instead of seeing something isotropic, there is some kind of squashing because galaxies are falling towards the overdensity, and therefore their peculiar velocities, basically because of a Doppler effect, they change the redshift that we measured. Now, if we study how this squashing actually happens, what we're really probing is how structures grow as a function of time. And that allows us to test models for modified gravity, for example. So from the spectroscopic data, we'll use these two things, baryon acoustic oscillations to pick, and redshift space distortions, essentially, so the shape of these distortions, because we see galaxies in redshift space. Now let's move to the photometric side of things. First is weak lensing. Now we have galaxies here with the original shapes that are very far away, and we are here as observers. But in any relativistic theory of gravity, we know that photons basically follow geodesics, and these geodesics will be distorted because of all the large-scale structure that's between the original sources and us as observers. So by basically correlating, studying how galaxies are distorted, their shapes, here we can basically extract information from all the matter distribution along the line of sight. So this is a great way first to get information about the density of matter in the universe, but also to understand how structures grow as a function of time. Another probe that I like very much is galaxy clustering again, but this time with photometric information. So the problem is that if we have spectroscopic data, usually we're looking at something like this. So this is the galaxy position on the sky as a function of redshift, and you see that we recover all these, the cosmic web, basically all these filaments, all these clusters, these voids. And here is where we measure BAO and RSD. Now, if we have photometric information, it means that our precision on the redshift determination will be lower. So there will be some kind of smoothing along the line of sight. We'll lose the radial resolution and we'll end up with something like this. Now, let me just say that this is like a super idealistic case. This is a precision close to what the PAUS survey does. Many people here were also involved in that. And it's even better than what Euclid will be able to do. So naively, one would think, well, there is no information left here. But actually, that's not true. And again, the DS collaboration did an amazing job showing that you can actually extract information from this type of probes. Because you have a lot of objects, and also systematic uncertainties are different. And when you combine with the other probes, this is still a source of cosmological information. So nowadays, when we say photometry in a cosmological analysis, we always refer to 3 times 2 point, which is basically a combination of 3 probes, but are usually we usually consider 2-point statistics as observables. So we can correlate the shape of galaxies, that's wave lensing, the position of galaxies, galaxy clustering, photometric, and the cross correlation. So we cross correlate the shape of background galaxies with the position of foreground galaxies, which is also called galaxy-galaxy lensing. And when we do the full combination, that's 3 times 2 point. Now, Euclid, if you remember at the beginning, I said that there are 2 instruments on board, VIS and NIS, to do both photometry and spectroscopy. So since day 1, Euclid was designed to perform both surveys at the same time, so photometry and spectroscopy. So the baseline that we have right now is to do the combined analysis with 3 times 2. This comes from the photometry side, and then BAO and redshift space distortions, so spectroscopic galaxy clustering coming from the spectroscopic side. Now, both surveys will probe the same volume of the universe, or they will significantly overlap in terms of volume of the universe. But we have very good reasons to think that actually we can combine them, assuming they are independent. I will not go into the details, but if anyone is curious, I'm happy to talk about this. Now, before showing you what Euclid will, or what we hope we will be able to do with Euclid data, let me just give you an idea of what's the current status using stage 3 galaxy surveys. Here I'm going to base my discussion on this plot. This is from the KIDS collaboration, not a stage 3 survey. And let me just focus on the blue contour here. So the blue contour is low Z, no DESI plus CMB. What that means is you combine all the galaxy surveys at low redshift, meaning KIDS, DSY3, DSY6 was not yet available at that time. And you combine redshift space distortions from EBOS. So let's remove DESI for the moment. DESI is stage 4. Let's just stick to stage 3. And we combine with cosmic microwave background, which is South Pole Telescope, the Atacama Cosmology Telescope, I guess C stands for, and Planck. And we get this blue contour. So if you look at the uncertainties, well, that's 0.32 on W0 and 1.15 on WA, which is good, but not super concerning, but still, it's nice. Now, then after stage 3, there was stage 4. And these were the first results that came from DESI, from the Barnard acoustic oscillations in particular, if you look at the dash contours. And here I'm not interested in this shift from the cosmological constant. I'm just interested in the size of the arrow bars. These were like 0.06 on W0 and 0.3 on WA when you combine DESI, CMB, and type 1a supernovae. So you see there is quite a significant improvement already. And this was even improved a bit more because these plots are for the first data release. In the second data release, they improved them a little bit. So if we just go back to the previous plot and now focus on this pink thingy, or violet, whatever it is, these are the best constraints that we have right now. We are still waiting for DS because they are not public yet, but I know they're almost ready. But except for that, if you combine all the low redshift galaxy surveys, meaning KIDS, DS, Y3, DESI this time, EBOS for the redshift space distortion, you combine with all the CMB probes that we have, and you combine with type 1a supernovae, you get this violet contour. So you see now the uncertainty is quite impressive already. It's 0.052 on W naught and 0.19 on WA. So that's the current status. Now let's see what Euclid can do. And for us to understand how Euclid will be able to provide very nice constraints, let me just show you some numbers first. Let's start with the spectroscopic analysis. Here I'm showing you the number of redshifts as a function of the volume that's probed. These are stage 3 surveys. These are stage 4. You see all the DESI points. This is Euclid. So Euclid will observe a huge amount of objects and probe a very large volume, basically more than 10 to the 7 galaxies. And if we move to the photometric side, here you see the galaxy distribution as a function of redshift. These 3 lines are for 3 stage 3 surveys. And this is the expectation for Euclid. So not just we will get like 5 more times objects at low redshift, but we will also be able to extend the tail of the distribution, so to basically probe objects that are at very high redshift. And for weak lensing, for example, which is an integrated effect, we are very much interested in these objects here. They contain a lot of information. Now, just another way to put it, here I'm showing you one of the observables that we use typically for weak lensing. And you see these points with the arrow bars. This is for kids, DSY3, HSC. The black lines, they also have arrow bars, but it's almost impossible to see them. Those are the expectations for Euclid. So we really expect much more precise measurements for many more objects, essentially more than 10 to the 9. And this is the latest official focus that we did in the collaboration. Now you see a lot of contours. These 3 colors are for different cosmological models, not that important right now. What you can see, this is spectroscopic clustering. Okay, we get some contours, fine. Now this is for weak lensing, but the nice thing I want to show you is that when we combine, this is 3 times 2. Now it's difficult to see if we just look at the contours, but if you look at the axis, you see that here we go from -4 to 2 and from -2 to 0.5. Look at the change of axis ratio here. So these contours are really much, much smaller. It's when we combine the different probes that we get these super nice constraints. And when we combine everything, spectroscopic and 3 times 2, we get these beautiful contours at the end. So in terms of numbers, here you have the exact values. Of course, this is a focus. This depends on many assumptions. The other thing that I show you is real data. But the take-home message is that if we combine all the main probes from Euclid, we will get constraints that are even more precise than what we have nowadays, combining all the cosmological probes available. Meaning, just with spectroscopic galaxy clustering in 3 times 2, these constraints are smaller than the ones I showed you before, combining DESI with CMB, with Pantheon, with all the galaxy surveys, stage 3 galaxy surveys. Now imagine once we combine these with CMB and diagonal supernovae, if there is a deviation from -1, 0, and there is something pointing away from a constant for dark energy, definitely we should be able to see that. And I just focus on dark energy my entire talk, but we can also put very nice constraints on all the parameters of the standard model for completeness. Now, this was for the main probes of Euclid, galaxy clustering, spectroscopic, and 3 times 2, photometric, but there are many other cosmological probes that are very interesting. So, for example, we can combine with the cosmic microwave background, not just doing the naive combination with a primordial CMB, but actually doing the cross correlation, meaning we use the photons from the CMB as our sources, and we look at the lensing on effect when they travel through the large scale structure. We can also look at galaxy clusters. We can look at voids. There are many different types of things we can do. And I just wanted to show you this focus that was done a few years ago to give you an idea of the power of combining with the CMB. So this is for the standard model. This is for the standard model with these 2 parameters for dark energy. And what I'm showing here is how constraints improve when you add CMB lensing with something looking like the Simons Observatory, and how they improve when you combine with the CMB, also adding the primordial CMB, so all the CMB information. And you see that for some parameters, like the matter density, for example, you improve constraints by 50%. For the dark energy equation of state parameters, you can also improve constraints by like 30, 40%. So there's still a lot of information there. And in the collaboration, we are also looking into all these points, trying to extract as much information as we can from the data. Another thing that I wanted to discuss here is that everything I said for the moment is 2-point statistics. So we're looking at correlation functions of 2 points. But we can also go beyond that and look at higher order statistics. So one can combine between 2 and 3-point statistics, or we can do even fancier things like simulation-based inference, field level inference. Marco here is very active on that front in Euclid. But for the talk, I'll just stick to 2-point. Now, before showing you what we've been doing with Euclid, I just wanted to show you this plot because I like it very much. Euclid is set up to do cosmology. That's the main goal. And one thing that we have in cosmology is that there are neutrinos, and we still don't understand many things about neutrinos. Euclid was really not supposed to say many things about neutrinos, or not on its own, basically, because it was more targeted to dark energy and the gravity model. But still, thanks again to combining with different probes, Euclid will also help us better understand neutrinos and also other particles beyond the standard model of particle physics. So here in this plot, you see the sum of neutrino masses as a function of the lightest neutrino mass. Now you see that this is the current constraint from Planck. This is our focus for Euclid, so a bit better than Planck, so it's not useless, but still. While we combine Planck with external data, meaning data from lower redshift, this is what we get. And this is our prediction combining Euclid with Planck and Euclid with future CMB data. Now let's assume that the universe has total sum of neutrino masses of 0.06 eV. And let's assume that the universe decided to use normal ordering for neutrinos. That means this blue line here. This is how the sum of neutrino masses depends as a function of the lightest neutrino mass in normal ordering. Now, what we can see in this plot is that when we combine Euclid and future CMB data, these are the constraints we'll get. So this means that there will be a tension at 2.5 sigma with inverted ordering. So if the universe had 0.06 eV as the sum of neutrino masses and it decided to use normal ordering, then we could basically test whether inverted ordering still works or not. So Euclid was not designed to do this type of analysis, but still, the data that we'll provide is so nice that in combination with others, we might be able to say things about some parts of physics that we really we're really not thinking about this. I'm just going to skip this one. Good. Let me just go to the last part of the talk, which is, okay, Euclid's been launched almost 3 years now already. What has happened? Well, the launch was the 1st of July, 2023, from Cape Canaveral in Florida, with a SpaceX Falcon 9 rocket. And Euclid is orbiting the second Lagrange point together with James Webb, Gaia, and plenty of people. This is the very last image, very last picture that was taken from Euclid before launch. And this is the launch that was really very successful, and we have a lot of fuel left. Now, the first thing that happened were the EROS. So these are the early release observations. There were 2 sets of them, one in November 2023, so you see quite early after launch, and one in May 2024. These were just 24 hours of observation to some allocated targets. So basically, they used 24 hours to take 10 pictures. And from these 10 pictures, this was mostly to show the capabilities of Euclid, to see how good the images are and the amazing science that's to come. But already from these pictures, there were many scientific results that appeared. And here I'm just showing you one of them, which is the Perseus cluster. And I think it's a very good example to, well, I'm projecting on the screen. If you look at, the slides, they look a bit better, but you can zoom in and still see features of faint galaxies. Well, not this one. This one is quite close, but you know what I mean. So the thing is that Euclid's images have so high resolution that you can zoom in many times and you can still resolve a lot of objects and identify a lot of features. Then there was Q1. That was the quick data release number 1 that took place in the 19th of March, 2025. And this was to give like a first idea of what a Euclid cosmological survey will look like. It was just around 60 square degrees. And I checked this last Sunday, so maybe there are a few more. But last Sunday, there were 52 scientific papers using this data set already. Unfortunately, none doing cosmology for the moment. Everything is legacy science, people looking at Milky Way. Well, not for these papers, I think not. But galaxy morphology, protoclusters, all these type of things. And this is another image. This one, I took it from the given field of Euclid, which is the Euclid Deep Field South. And the interesting thing is that I zoomed in 70 times to get this picture. And you can still see that, you have a lot of resolution left, even after zooming in 70 times. So that's telling you that for every picture or every image of Euclid, there's a huge amount of information there. Good. Now we're working towards the first data release. So if you go into the ESA website and you look for Euclid timeline, this is public and it says 21st October 2026. Now this will probably not happen, but still in the website, that's what it says. But the first data release, that's where the first cosmological analysis, cosmological results from Euclid will come from. And this is the expectation. So we will see around 1900 square degrees. This is the same image as before. You have the galaxy, the ecliptic plane. These green patches are the expected Euclid footprint at the end of the mission. These blue patches, this is the actual DR1, the first data release footprint, at least the patches that have been decided to go into the first data release. So you see we recover the 1/3 in the north, 2/3 in the south, more or less. Now, what we're doing now in the collaboration is to basically, we're doing a lot of data validation. So we have access to the data, but instead of looking at everything, we want to be as blinded as possible. We want to avoid confirmation bias, because if we unconsciously try to find something away from lambda CDM or try to recover lambda CDM, that could impact the choices that we make in our analysis, and we don't want that. So what was decided was to select a subset of DR1, which is called TR1, which stands for training DR1 or something like that, with more or less the same ratio. So 1/3 in the north, 2/3 in the south. And this is still compatible with the policy for blinding that's been adopted in the consortium, in the sense that we can do many things, not everything, but we can do many things in this data set to make sure that data is looking fine. And these would be these white patches over here. So we are doing plenty of tests, measuring all types of consistency checks and trying to see whether there are any systematic effects left or not. Now, another thing we're doing in parallel is to basically prepare the inference pipeline. So to stress test all the pipeline, all the interfaces, and to discuss all the modeling choices, all the analysis choices, basically to be ready once the data is there, fully clean, we can measure our observables, and then we can run the analysis. Now, we do this in multiple defined key projects within the consortium. There are multiple projects that have been defined. Each one is in charge of different parts of the analysis. But in particular, there is this joint cosmology key project that we coordinate with Martin here and Melita. that basically puts together everything with the goal of providing the final results, final constraints of cosmology. Now, I just put here a very schematic idea of the entire pipeline, and I will quickly guide you through it. So the idea is that, well, the goal is to get the cosmological constraints. That's the thing. Now, in a standard likelihood analysis, we usually need three things: a data vector, something we measure, a prediction, and a covariance. So for the data vector, we rely on a code called CloyLeap that we are developing. I'll say a few more words about this in a moment. Now, for the data vector, there is an entire infrastructure pipeline. There's a huge pipeline in the consortium, which is called the science ground segment, where they take the raw data coming from the satellite and they do all the processing until the measurement of the observables that we're interested in. Now, we're going to take these measurements, and then we're going to plug in a covariance to basically account for the uncertainties. Now, for these, we are going to use different codes, but for the 3x2 point part, the analytic covariance will come from a spaceborne, and we have Davide here, who's the main developer. And there is also Euclid Leap. We are going to use Euclid Leap to basically read and write all the products. So even if it seems trivial, it's very hard to make sure that all these boxes use the exact same formats and that they can talk to each other. So we're going to use Euclid Leap for that. Now, once you have the three ingredients, you can put all of them together into a likelihood. Now we use CloyLike that we're also developing for this. And once you have your likelihood, then you can sample with whatever sampling method you prefer, and you get the cosmological constraints. So this is like the overall idea. Now, I just want to say a couple of things, mostly to give credit to people, because this is not really my work. So for CloyLeap, this is a code that we are developing that basically computes the prediction for the observables that we're interested in Euclid. Now, it's about to be public. It will be publicly released very soon. So if you need the code to compute cosmological predictions, I encourage you to use this. It's flexible, efficient. It's nicely integrated with different Boltzmann solvers. It also uses these JAX-based frameworks to be able to use this automatic differentiation and speed up the analysis. And it's basically being maintained by these 6 people here, plus a lot of contributors that are actually contributing weekly to the code. Then for CloyLike, this is the code for the likelihood. Again, maintained by these 6 people, plus many contributors. Euclid Leap, this is developed by Guadalupe Cañas Herrera, and Spaceborne by Davide, as I said before. And I just wanted to show you this plot that I stole from Jose here. So if you have questions, you go to him or Martin. Sylvain also contributed to this work. Sylvain was also here for many years. And this is just an example of the end-to-end inference pipeline. Just to show you that we are basically working on stress testing this and discussing all the modeling and analysis choices. I'm not that interested now in the size of the contours or anything like that. This is just to show that the pipeline is in place and that it can run. Because in this case, the measurements were done with one of the codes that we use in Euclid. This was done on a simulation based for Euclid, the flagship tool, where Francisco, Pablo were massively involved. Predictions were done with CloyLeap, the code that we're just talking about, covariance with Spaceborne, the code that we will use in the analysis, and the likelihood with CloyLike. So you see all these are tools that will be used in the real data analysis. So we do have a pipeline, and we are basically stress testing this. And this is just my last slide. So there are some tensions that started to appear in the standard model. Especially, I like very much this evolving dark energy. But even if that was not there, the nature of the dark components remains still unknown. So it makes sense to try to test even more this model and try to better understand what's going on. Now, Euclid will provide very precise measurements that will allow us to perform galaxy clustering with lensing analysis. And with this, we will be able to shed some new light on the dark components of the universe. One important message that hopefully I've managed to convey is that probe combination is really key in cosmology and particularly in Euclid. So we really need to combine different probes to extract the maximum amount of information from the data, and that's why our baseline is already galaxy clustering from the spectroscopic side and 3x2 from the photometric side. We're also considering other cosmological probes because that will just increase even more our constraining power. And looking forward, we are now first doing all the data validation, testing the pipelines, and discussing all the choices that will go into cosmological analysis. So just stay tuned for the cosmology results with Euclid year 1. I'm sure we'll give plenty of seminars about this when the time comes, but it will still take a few months. And I'll just stop here. Thank you.
Okay, thank you. Very nice talk. Have time for questions.
You don't like the plot.
No, I wanted to ask if can you say please something more on why we can consider that the photometric and the spectroscopic groups can be analyzed, assuming that they are independent?
Yeah, so naively one would think that you cannot because you are probing the same volume, right? So the information is already there. So if you're looking at it from two different angles, there should be some correlation that you should account for. Now, in Euclid, we have some particular case, which is that our spectroscopic sample starts at high redshift, like above redshift 0.9. Now, the weak lensing probe, what you're really sensitive to is halfway through your sources. Meaning when you use weak lensing, even if although it's an integrated effect, you get the most efficiency basically at halfway, so the intermediate redshift. And we're gonna have sources up to redshift 2, 2.5. So intermediate redshift, that's 1. So in terms of redshift overlap, spectroscopic will probe the high redshift universe, photometric will probe the lower, let's say, redshift universe. But still, if you compute analytically what's the correlation, and if you do that in Fourier space, for example, the modes that you are actually probing with the spectroscopic survey are not the same modes that you're probing with the photometric one. So even if the volume is the same, in Fourier space, you are probing different modes with the two different data sets. And in the worst case scenario, by removing some scales in one of the probes, you can make sure that the probes that are being used in each one of the modes, that are being used in each one of the probes are not shared. And if they are not shared, you can treat them as independent. Now, this has been tested also by DESI in configuration space, and they found that for DESI DR1, combined with weak lensing data, the correlation was negligible. But still, this is like hard-coded. I mean, it's imprinted in the final results, right? If you combine everything, you say my baseline is the combination, and I assume that there is no correlation. If this assumption is wrong, then basically your final cosmology is wrong. So we are checking this also in Euclid, but we have very good reasons to think that it will be negligible.
Well, thanks for the very nice talk. So you mentioned how much basically you compared the analysis from the photometric clustering and when you add spectroscopic clustering properties.
Yeah.
So for some of the parameters didn't make much of a difference from what I saw in sigma 8 omega matter.
This one
It's a previous
plot.
So in this one, it doesn't, for the question of a state, doesn't make much of a difference, maybe.
Yeah, I mean, constraints reduce a bit, but it's true that what's leading the constraining power is 3 times 2 point. Now,
For
yeah.
For other parameters, I guess it makes much more of a
For other parameters, for example, the Hubble constant, the spectroscopic clustering is very sensitive to the Hubble constant because it changes the wiggles in your power spectrum, right? While 3 times 2, weak lensing don't see them at all. And photometric clustering, you have like a smooth version of them. So it's very hard to put constraints on H, for example. The same for omega B, or the baryon density. now for this exact plot, this is a focus at the end. So there were some assumptions that were done in each one of the probes, like what scales can we use, where the range of scales where we think the model will still hold. This is something that needs to be checked in a lot of detail when we do the real data analysis. So we'll see how one compared to the other behaves in the real data scenario. But yeah, for some parameters, it's useful to have one or the other probe.
More questions? Okay, then let's thank Isaac again.
Thank you.
We can go to the pizza.